In the previous section, we've kind of hand-waved our way through to an expected value for this number of characters before we see a certain string appear for the first time. And that's good enough in this case where the difference is so extreme to get a qualitative statement. But suppose you want to assign a specific p-value or a probability to, if you found an open reading frame of length 400, is that significant enough or not? It's substantially longer than the expected open reading frame in random DNA. But the expectation alone is not strong enough to give you much more. You could use maybe Markov's inequality, but the bounds are very weak from that. So in some cases, and in this very simple null model specifically, we can get more. We could get almost the full distribution of the number of letters until the stop codon comes. And I want to just briefly introduce a bit the mathematical tool you can use for that. And it's a cute tool in its own right, so maybe you enjoy it. The tool is a generating function. I wanted to ask you about whether you've seen it, but it's only 5 minutes left, so I'm going to just introduce it, and not much more that we can do today. It only works if you have a random variable that has integral values and non-negative values, or at least you could maybe shift it. But say here, it's only natural numbers. That's the possible outcomes of your random variable. In our case, this would be the number of characters, right? Until we see the stop codon, so it certainly qualifies for this. Then we can write down this weird thing. The probability generating function, it's the infinite series where we sum over all possible values for this random variable. Then we take the probability that x attains this value k and multiply that with a symbolic variable set to the k. So in principle, this is just a power series, or just some, you can interpret it as a function of z, a real or complex function of z. And we'll mostly treat these as just symbolic algebraic objects to calculate with and use some equalities that make life a bit easier. What do I mean by that? Specifically is this one. That's one of the simple consequences just of the definition. If you have the generating function, the probability generating function of such a random variable, you can compute the expected value by taking the derivative and inserting 1 for z. That's wild. How's that? Why is that? Or where does that come from? That part is very easy to prove. We look at, first of all, the expected value of x. By definition is just this sum over all possible values. Then the probability that x attains this value times k, right? That's the expected value as you've defined it for discrete random variables. Now, let's also compute what this derivative is. And let me first leave z symbolically. Now, the piece of knowledge that we use here is that power series, if you can either argue with function theory, or you treat it as an algebraic object, or you treat it as a Taylor series. Either way, you can take the derivative of a power series by taking the derivative of each term. It's a bit like for finite sums, this is always true. The derivative of a sum is the sum of the derivatives. It's not obvious whether that's always true if the sum is infinite. Sometimes these things break, but here it doesn't. So you just take the derivative d dz of this term in the sum. And what's this derivative? Well, this probability, it doesn't depend on z, so that's just a constant. So this thing is the probability And this thing, well, that's a polynomial. I know how to take derivatives of that. It's k times z to the k minus 1. Right? That was easy. Now the sum in front stays. So you've turned one power series, this one, into a new power series, this one. And it just has slightly changed terms. And now if you insert z equals 1, this guy just goes away. And what's left is exactly the sum of the expected value. So it's kind of obvious when you write it down. The reason why it's useful is that if you can write a closed form for this infinite sum, it might be much easier to use whatever computer algebra or your high school math calculus knowledge to take the derivative of these functions and insert 1. That's a simple operation. And you can go further. You can also get the variance. This needs a slightly longer calculation than this, but only twice as long. But maybe we'll postpone that. And then you get the variance. All you need for that is the same ingredient, first derivative at 1, and you need the second derivative at 1 as well. But these are usually also easy to get. And in particular for our concrete ones. We'll look more into this next time. But let me just show you here again as a kind of preview how you could use this. Forget the calculation of how you get the generating function here. You can essentially go from the automaton again. And I'll explain this next time in a bit more detail. Sorry, super small. Doesn't work. Can I zoom in? No? Okay, sorry, it's a bit small. One thing about Mathematica is that the interface is not so great. You can calculate the generating function. It's this simple rational function. So taking derivatives is not too hard. And you can take the derivative. You find the 64/3 again, as we've had. And you can compute with this formula the variance, which is, well, this number. What's more interesting or more intuitive is the standard deviation, which here is 18 2/3. And so from these two, you can already get a much stronger quantitative statement of how unlikely it is to see an open reading frame of length, say, 400.